Today, we're going to be solving a popular system design question, Design LeetCode. You may also see this question in the form of designing any other online code submission platform. The key to system design is to systematically break a question down into easily digestible steps. These are the simple steps that we are going to go through today, and by the end of this video, we will have come up with an efficient system. If you want to follow along and solve the system, the problem details are in the description. And you can also check out our website at systemdesignschool.io, where we will have tons of system design problems, as well as our very own AI auto grader that will provide you feedback on your solutions. The first thing that you want to do when trying to approach any system design question is to first understand what the requirements of the system are. For this question, we're given a bit of information about its functional requirements, so let's make sure we understand them. We're told that there's a question bank. Users can write, compile, and run code against test cases, and that users can compete in contests for a spot on the leaderboard. This tells us that there are two clear functions this system must have. It must have a code evaluation function where users can solve questions and have the code they write evaluated by the system. And it must also have a contest system where users can participate in contests and get ranked on their speed and accuracy. One thing you should also note is that even though it's not explicitly mentioned, if we have users, we must have some kind of user sign-in/management functionality as well. Other than functional requirements, we should also determine some of the non-functional requirements. Most of the time, this will not be provided, so we have to make some decisions ourselves. There is no exact right or wrong answer here. It's all about making thoughtful insights. One thing you should always consider are the latency and availability requirements. In this system, we will need low latency because our leaderboard will need to be updated in real time as users submit. We will also need high availability as our code submission needs to be working at all times. One additional insight I've made is about security. Users should not be able to run code that poses a threat to our system. Now, we can move on to the next step, which is resource estimation. We will be calculating two main resources, queries per second and storage. For queries per second, we want to know the maximum load our system will have to handle. The two operations we care about are our read queries per second and write queries per second. To calculate it, we need to identify our bottleneck. Of our three main services, which one is likely to have the most operations? It's clearly not user management because users don't change their profile that frequently, so we can rule that one out. For our contest, we will have to update the leaderboard every single time a user makes a submission. However, there is only one leaderboard update per submission. But for every submission we have, there are 20 test cases that get executed. This tells us that code submission is our bottleneck. Now, it's just simple math to calculate our exact queries per second. We're told that there are 10,000 users per day and 20 submissions per user. That comes out to 200,000 submissions a day. For each one of these submissions, we have 20 additional test cases that run. This comes out to 4 million test cases executed in a day. We don't want this in queries per day though, we want it per second. Because we're told that each contest runs for 2 hours, which is 7,200 seconds, we can divide 4 million by this amount, and we get our queries per second, which is roughly 556. You may be wondering, is this our read queries per second or our write queries per second? Well, just think through what these actually mean. A read operation is when we just retrieve data, whereas a write operation is where we add or modify data. In this case, running a test case does not create or modify any data, so this 556 is our read queries per second. Fortunately for us, the problem tells us that the read to write ratio is 100 to 1, so we can calculate our write queries per second as 5.56. Now, moving on to storage. Let's identify what data we are actually storing. We will need to store user information, contest information, user submissions, and test case execution results. User and contest information is mostly just going to be string data, which takes up trivial storage, so we can safely ignore them. The other two are again just basic calculations. For user submissions, we have the scalability requirements in the problem to help us. We know that we have 10,000 users and each user makes 20 submissions per contest. As each submission is about 100 kilobytes, this means our total data for submissions in a day is 200 megabytes per day. In a month of time, this comes out to 6 gigabytes per month. Now moving on to our test case storage. We know from the problem that there are on average 200,000 submissions a day. Each submission has 20 test case results and each result is 10 kilobytes. This comes out to 40 gigabytes per day and in a month of time is 1.2 terabytes. Now that we're done working with the numbers, let's move on to the bread and butter of every engineer, API design. It's really up to you how many APIs you choose to design. For the sake of this video, I'll design the two that I think would be used most often. First, let's start with an API to handle code submissions. I'm going to use HTTP as a protocol, as this is the universal standard for internet communication. As for the method, for each new code submission, we want to store it in the database. This is best handled by the post method. Our endpoint URL can really be anything we want, as long as it makes sense. In this case, something like what's shown on screen makes the most sense. As this is a post method, we need to provide a request body to actually provide data for the API to process. For each code submission, what data actually matters? Well, we need to know what user submitted it, so keeping track of the user through a user ID might be good to include. We also need the actual code they're submitting, which we can save as a string, as well as the language they wrote it in so we can compile it properly. What should the API send back to us? This is our response body. We want to be able to tell the user if their submission succeeded or failed, so we can return the status of their submission. We should also return whether or not each individual test case passed or failed. There's one API completely done. Let's move on to what I think is the next most used API, which would be fetching the leaderboard. Again, I'm going to use HTTP as a protocol. As for the method for this API, we aren't actually creating or modifying any data. So we can use a get method, and our endpoint URL could be something like what's shown on screen now. As this is a get method, we don't actually need a request body as we're not giving any data to the API, only receiving it. So we only need a response body. For viewing a contest leaderboard, the most important thing is to return the ranking of all users. This ranking should include all the users on the leaderboard, as well as their scores. Now we have two well-designed APIs for the system. Of course, you could come up with more, but for the sake of this video, we'll move on to the next section. Now, let's design our LeetCode system. First, we know that we have a client who will be interacting with our services. This is the most simple representation of our system. Let's start to make this system more efficient. Let's separate our main services into modules. For us, we know that the main functions are managing users, code submission, and contests, so we can make these our three main service modules. We also know that all these services will store data, which means they each have to have databases. Now that we've fragmented this a bit, let's try to address any weak points. From earlier, we know that code submission is our primary bottleneck, so let's see if we can make that handle queries a bit better. There are many different approaches to handling queries more efficiently, and many of them are acceptable answers. For this, I am going to go with a simple approach, which is implementing a message queue. Our code submission service will accept the user-submitted code and then queue them as messages into our message queue. We will have code execution workers fetch from the queue, extract the user code and identify the language, which we sent in the API, and run them against the test cases. We know that we will have a lot of test cases to run, so one way to make our code execution workers efficient is to have them reside inside Docker containers, as they provide efficient load management and can be tailored for different languages. For example, we might have a few Docker containers run all the Python tests, while some others may run all the C++ tests. After the test cases have run, the workers will write the output to the database. There's our biggest headache solved. Our other big headache is handling our contest leaderboard. We need to update our leaderboard with results, and also display them to users in real time. Well, for updating our results, we have a system for that already. We can just have our code execution workers update the leaderboard when a user has a valid solution. As for showing our leaderboard to users, we know that it will need to have low latency, which informs our decision. In our current system, we are fetching the entire leaderboard every time we navigate to the leaderboard API endpoint. This is very inefficient. We really only need to fetch the most recent changes, as the rest of the leaderboard will stay the same. One way we can do this is by using an in-memory data store, such as Redis. Storing our leaderboard in memory allows us to make much faster read and write operations compared to storing the leaderboard in disk-based storage. While we will still update our main contest database, we want the in-memory data store to be doing the operations quickly so that our users can see real-time changes. In fact, Redis has a data structure called a sorted set, which will automatically rank the users by their scores, allowing for very fast leaderboard updates. In any system design interview, you will be asked some further questions to test how well you can handle the problems that may come up. Let's tackle a couple that would be common for the system. First, how would we prevent users from submitting malicious code that messes up our service internals? As with anything that runs code, there's always a risk that people will write malicious code that will do bad things to our system. However, one way to mitigate this is using our Docker containers. Each container is isolated from the system, so any malicious code will only be accessing temporary storage within each container, preventing any actual damage. Another good question is, in what format should the test cases be stored, and how should they be used? Each test case has an input file and an expected output file. Each problem has a driver code for each language that parses the input file. When the user-submitted code is executed by the Docker container, an output file is created in a temporary folder mounted on the container. The output file can then be compared to the expected output file for correctness.